Hello, welcome to Maths with EJD. In this video, I'll be talking about graph properties. Okay, but then before I do that, you remember in the first video, I talked about introduction to graphs, and the last part of that was, there we talked about representation of graphs. How are graphs represented, right? Representation of graphs, and we talked about uh, adjacency list, which was quite clear. Adjacency list. We talked about um, another one, which is matrix, adjacency matrix. And then we also talked about incidence matrix. But I mean, my explanation for incidence matrix wasn't that clear. So I want to quickly take care of that before I move on to matrix properties here. So of course, we already know about adjacency list. But I mean, let me, for the sake of clarity, imagine you have A, B, C. Is this the way it goes? I think A, B, C, D. Like, is it this way? Let me see. Or whatever. I mean, based on this, we'll just do what we have to do. Yeah, I mean, I think it's like this. So we have A, B, C, D. So if we want to use adjacency list, right? What we just do is this. Okay, we just have for adjacency list, we just have take each node, you have A, and list the other nodes connected to that. So connected to A, you have B, C. Okay. Then next, take node B. For A and for A is connected to B and C. That's what we have B and C. For B now, B is connected to A and D. So we have A, D. Okay. If you take C, C is connected to A and D. Okay. Uh Oh, C is also B is connected to A and D. C is also connected to A and D. Okay, that's fine. And then lastly, we take D. We take D, and D is connected to B and C. So that is the idea of adjacency list. Okay. Now let's talk about adjacency matrix. Of course, that was quite clearly explained, but I mean, just to buttress the point again, for adjacency matrix, so here now you have you list out the vertices A, B, C, D. Okay, like we have there, and then you also have this A, B, C, D. So like rows and column kind of thing, like that. So if there's a line between A and, of course, all the I mean, this will be zero straight. B, B, C, C, and D, D. All of that will be zero. Sure. Then, having taken care of that, so any two vertices that have a line joining them, that will be one. So A and B has an edge joining them. So AB, this will be one. Then A and C also has, this will be one. Then A and D doesn't have, that will be zero. Okay. Then B and A, of course, A and B means B and A, so we just have one. Then B and C. B and C has nothing joining them, so you have zero. B and D has a line joining them, so that's one. Then C and A. Of course, AC means CA because AC is one, so CA is also one. Then AB, no, there's a line joining AB, so you have one here. AD, there's no line joining AD, so we have zero. Okay. I guess I want to move this one down a bit. Okay, this is DD down here. Then AD is zero. So of course this is zero also. There's no line joining D and A for sure. Then BD, there's a line joining BD. So we have one. There's a line joining CD. That's also one. So this is the idea of so we have 0, 1, 1, 0 for that one, right? 0, 0, 1, 1, 0. So this is the simple idea of adjacency matrix. Now, how about incidence matrix? Incidence matrix. So we have incidence matrix. So, I mean, this wasn't clearly explained in the first video. So for incidence matrix, right, take the rows as the vertices and take the columns as the edges. So this will be edge AB, edge AC, edge BD, edge CD. Those are the four edges we have, right? That was called E1, E2, E3, E4 in the previous video, right? So you have edge AB, there's an edge AB, right? There's edge AC also. There's edge, is there edge BC? There's no edge. Yeah, there's edge BD and then there's edge CD. Yeah. So if A if A is actually, of course, I mean, I think it's very simple instead of even telling too much stories. So clearly, if you find if this vertex is part of this edge, then it is incidence to the edge, right? So A is incident to AB. Why? Because here you can even find A. So A is incident to AC. A is not incident to BD, so that will be 0. A is not incident to CD, that's 0. Then B is incident to AB, all right? That's 1 because you can even find B. B is not incident to AC. B is incident to BD for sure because there's B there. B is not incident to CD, that's 0. C is not incident to AB, 0. C is incident to AC, that's 1. C is not incident to BD, 0. C is incident to CD, that's 1. Then D is not incident to AB, D is not incident to AC, D is incident to BD, D is incident to CD, and that is exactly the idea. So the rows are the vertices, while the columns are the edges, and that is how you have adjacency matrix. All right, so that's settled. Now, um, let's move on to what this video is about, and that is the idea of graph properties. I guess I want to breeze through that. Let's talk about graph properties now. Graph properties. Okay. So here, the first property we want to talk about will be the degree. How do you talk about the degree of a graph? So, and here we talk about in degree and out degree. In degree and out degree. The concept is very simple to grasp. Um, okay. The degree, the degree of a vertex in a graph is the number of edges, is the number of edges connected to it. Basically, that's the degree. The number of edges connected to it. That's all. So in directed graphs, this this is further. So if the graph is undirected, you just count all the edges connected to the vertex, and that will be your degree. But if it is a directed graph, you now talk about in degree and out degree. So in directed graphs, um in directed graphs, is further this is further divided into in degree, in degree, and in degree is simply the number of edges, of edges the number of edges coming into the vertex, coming into the vertex. Okay. And then you have the out degree. Then you have the out degree. So for the out degree now, you have this to be the number of edges, the number of edges going out of the vertex, going out of the vertex. Okay. Okay. Now, well, I guess I been want to just do, let me just do some drawings, right? Or okay, I mean, let me just do, yeah, let me just do that. Sorry, I was contemplating. Okay, so imagine you just have, let me just do, you have a simple ABC. A B C. So this goes Okay, I mean, let me just do general, or I guess, can we just do the normal, can we just do the normal ABCD we've been doing? A, B, C, D. Let that just be our standard for whatever we have to do. So this connects, this is this is this. So here now, um, so the degree of this, the degree is actually connected to a vertex, right? So the degree for each vertex, degree, okay. I guess, or better we can do it this way. So we just have vertex or node, and then the degree. Okay, the degree will simply be whatever number of edges connected to it. So A, for each one, it's just two all through. So uh, you have AC and AB. So for B, it's also two. For C, it's two. For D, it's also two. Easily. Okay, that's for undirected graph. So this is a very good example for undirected graph. Okay. Then how about when we have a directed graph? We have a directed graph now. Same, I'm just going to use the same A, B, C, D. So here we have A. Okay, I guess I want to change this. So here we have A, B, C, D. A, B, C, D. A, B, C, D. So this, then this, and this now. Okay. So here now we have to talk about in degree and out degree. I mean, I just did this randomly. So we have the vertex. Let me use green to. So we have the vertex. We have the. So we now need to talk about in. We need to talk about in degree and out degree. Okay. Yes, I want to make it better. So you have the vertex. You have the in degree. You have the out degree. All right. So for A now, the in degree for A is zero, but the out degree is two. Okay. For B, the in degree is two, and the out degree is zero because you have two arrows coming into B, but nothing is going out. Then for C now, the in degree for C is one, the out degree is also one. Okay. So for D, you have the in degree for D is one, the out degree is also one, basically. So because for A now, nothing is coming into A, but something is going out of A to B, something is going out of from A to C. Then for B, nothing is for B, A something is coming from A and D to into it, nothing is going out. For C, A is going into C and it's going out into D. Then for D, C is coming into D and D is going to B. That's the idea of in degree and out degree. That's the degree of a graph, and it is connected to a node. So don't forget that at all. Okay, so let's talk about I mean quite a number of examples here. I'll just write one and I'll mention the other ones. In an undirected graph representing a social network, the degree of a person or node corresponds to the number of friends they have. Okay, I think we've done that before. So in a directed graph representing Twitter-like network, where edges represent follows, the in degree of a person is the number of followers they have, and the out degree is the number of accounts they follow. Okay, let's talk about. Okay, let me just give an example. Um, let's say examples, right? Examples. So for Facebook friendship. So for Facebook friendship, we have so the degree is the number of mutual friendship. The degree is the number of mutual friendships, mutual friendships a person has. Okay. And of course, that's like an undirected graph. Undirected graph. Okay. Then that's one. Another one is Twitter follows. I mean, now it's called X, right? So let's just call it Twitter follows. So, so in the case of Twitter follows, right? Um, in degree, the in degree of the person in degree is the number of followers a person has, okay? That'll be the in degree of the person. Then on the other hand, out degree is the number of persons, is the number of persons a person follows. A person follows. That's the idea of out degree. All right. So in a tournament graph where each pair of vertices is connected by a directed edge, the out degree of a team represents how many teams it defeated, and the in degree represents how many teams defeated it. Okay, I mean that's quick, easily understood with the Twitter example. So that's the idea. That's one property talking about the degree of a vertex in a graph, the degree of a vertex in a graph. All right, so let's go on to talk about something else, which is about paths, cycles, and connectivity. Paths, cycles, and connectivity. Okay, so here, quickly we talk about about paths, right? Paths are simply a sequence of vertices, a sequence of vertices connected by edges. Okay, sequence of vertices connected by edges where no vertex is repeated, where no vertex is repeated. So when a vertex is not repeated, of course, that cannot be a cycle. Because if you go back to where you started from, that would be like a cycle. So a very good example of this, a good example of this would be um in a graph, in a graph, in a graph representing cities, in a graph representing cities, those cities are like nodes or vertices, right? Connected by roads. Cities connected by roads. So the roads in this case are the edges. Okay. A path, a path from city A, a path from city A, a path from city A to city B lists the will list the sequence of will list the sequence of intermediate cities, a sequence of intermediate cities. That's a path. Okay. For instance, a very good example, I mean, in the Nigerian context, right? If you're traveling from Akure to Abuja, okay, traveling from Akure to Abuja, one pathway you can take is you go from Akure to where's that place now? Okay, let's just say I'm trying to okay, since you're talking about cities, right? So maybe Akure to Ibilu. I mean, that's what comes to my head right now. From Ibilu, maybe you get to Okene. From Okene, you get to Lokoja. And from Lokoja, you end up in Abuja. Okay. So that is a very good example of what a path looks like. Okay. Something like this. Then that's a path. Let's talk about cycles. Cycles, that's the next thing we want to talk about. Cycles. So because we're talking about cycles, paths, and connectivity. So talking about cycles now, um, so a cycle is actually a path that starts, it starts and ends at the same vertex, starts and ends at the same vertex. Okay. Without revisiting other vertices, without revisiting other vertices. So that's like a closed loop, basically. It's a closed loop without revisiting other vertices. So a very good example of this A very good example of this would be um, that in a graph of power stations, in a graph of stations, power stations, and say transmission lines. So the power stations are like the nodes of vertices now. The power and the transmission lines are the edges. So in a graph of power station and transmission lines, a cycle, a cycle can indicate, a cycle can indicate a redundant power route, a redundant, a redundant power route useful for reliability, useful for reliability. So you see, cycles have their importance too, but sometimes we don't desire cycles because they are like a closed loop. Nothing flows out, nothing flows in. Or I mean, it just things just keep moving around in the cycle like that. Then we talk about connectivity now. Connectivity. So connectivity simply indicates it. This simply whether indicates whether a graph is connected. It indicates whether a graph is connected. Um, that is, if exists, there exists a path between any two vertices, any two vertices. All right. That's what connectivity is. So if there's no path between two vertices, then the two paths are not connected. I mean, the vertices are not connected. So if every vertex is reachable, if every vertex is reachable from any other, from any other, okay? The graph, you say the graph is strongly connected. The graph is strongly, okay, you know how I do this. The graph is strongly connected, strongly connected, okay? That is in the case of that's in directed graphs, in directed graphs. Okay. Or we say they are just simply connected. They are simply connected. They are simply connected in the case of undirected graphs. So, um, okay, a- an example of this would be of this example, um, in a computer network, in a computer network in the computer network graph, connectivity, connectivity, connectivity implies all devices, all devices are capable of communicating. All devices are capable of communicating. And the internet is a very good example of this. All devices are capable of communicating. Okay. For instance, if you're in a room with a Wi-Fi, as far as you connect all your devices to the Wi-Fi, you can send WhatsApp messages to all the devices, right? Or you can send messages to all the devices over the internet. So that's a very that's connectivity, right? So if not, the network is partitioned. If not, the network is partitioned. The network is partitioned into isolated components. The network is partitioned into isolated components. Okay, so that is the idea of connectivity. So, I mean, the idea of this is, that same example of ABCD we've been doing. A, B, C, D, like this. So, this is like if you have an undirected graph, this is not strongly connected, right? Because when it becomes strongly connected, when you now have maybe something like this, then it means you can reach A from C, you can reach A from B, you can reach A from D, you can reach B from A C D, you can reach A from B C D, you can reach B from D from A C B, you can reach uh C from A B D. Okay, so now you can say this is actually connected because it's undirected, so we say it's a connected graph. You know, it's a connected graph. Yeah, I think that's the concept. Okay. But then, of course, we can still have the same thing. Say you have A, B, C, and D, and then you have this, okay, directed like the two directions goes, and then we have this and this. This is a strongly connected graph because it's directed, right? And every vertex can be reached from every vertex. So this is a strongly connected graph. Okay. So that is the idea of connectivity. Okay, so let's go on to um okay, the last set of ideas under properties, right? So far we've talked about degree, the degree of a vertex. We've talked about of course under that we talked about in degree and out degree. Then now we've talked about path cycles and connectivity. Then lastly, let's talk about subgraphs, induced graphs, and complements. Okay. Three, subgraphs, subgraphs, induced graphs, sub subgraphs, induced graphs, and complements. Complements. Okay. Um, so in this case now, let's start with a subgraph. What is a subgraph? Okay. This is simply a graph formed from a subset, to the graph formed from a subset of the vertices and edges of a larger graph, of a larger graph. Okay. So an example of that would be, say, um, in a transportation network graph, in a transportation network graph, a subgraph, a subgraph might represent the subway system, the subway system in one city, extracted, extracted from a graph representing all modes of transportation. Okay. Um, well, can I try? Okay, well, I think um I want to believe that's clear enough. But if I want to if I want to try, maybe I'll just do something like this. If I want to try, maybe I'll do something like this. Say you have A, B, C, D, E. I'm making it this large because maybe there's G here, and then you have all these connectivities happening all over the place. Maybe this also is there. So maybe you have all of this happening, right? Maybe this is everything like maybe maybe you can take a flight Imagine that you can take, let me say, let me show the possible flight path. Maybe you can take a flight from here to here. You can take a flight from here to here, and like this. Maybe you can take a flight along this path, and then on this other hand, you can on this other part still there's a rail network, rail network, rail network, rail network. Then maybe there's what else now? Let me see. Some of those places you can have like monorails. Maybe there's monorail, 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 and then probably some kind of there's also monorail here. And then in addition, maybe there's uh fly subway, right? Subway, like that. So if we just focus on just I mean the yellow is obvious now. So that yellow path now, that yellow thing you're seeing is actually like a subgraph, so to speak. If you focus on monorail alone. Yeah, I think that's pretty clear. Now let's talk about induced subgraph, induced subgraph. So we have subgraphs, induced graphs rather. Subgraphs, induced. Oh, it's actually induced subgraphs. Induced. So induced subgraphs. Okay. So let's talk about that. Induced subgraphs. So here, a subgraph formed by taking, it is formed by taking a of vertices, subset of vertices, and all edges between them, and all edges between them in the original graph, in the original graph. Okay, that will be an induced subgraph. So a very good example would be this um, from a graph, from a graph of people, from a graph of people connected by shared interests, connected by shared interests. The induced subgraph of chess players includes includes only chess players and their mutual connections, and their mutual connections. Okay. Imagine that you have, say you have, I mean, I'll just do this randomly. So you have cities 1, 2, 3, 4, 5, 6, 7. Okay. Or let's say people, right? People, since we talked about chess players. So we just have this kind of people. So it now turns out that these guys, people 2, 4, 5, 6, people 2, 4, 5, 6, like this, 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 they are the chess players. So what we are now saying is that that graph, that graph now is the induced subgraph is going to include all the a subset of the vertices. So the 2, 4, 5 are the subset of the vertices plus all the edges between them. So now this is like an induced subgraph. Basically, that's what this is. That's the kind of concept I think that should be portraying. Okay, so let's go for complement, which is the last part of this now. Subgraphs, induced subgraphs, and complements. Complements. Okay. So talking about complements now, this is actually a graph. It's a graph that contains, it's a graph that contains the same vertices. It contains the same vertices as the original, okay? As the original, but has has edges wherever, interesting, original, wherever the original graph does not. So it's yeah, I mean it's giving me the idea of the complement of a set. So it is the complement of a set is actually all the elements in the universal set that are not in the set, something like that. So, and a very good example of this would be um, that a graph, in a graph representing, in a graph representing friendships, friendships, the complement graph, the complement graph would show pairs of people, pairs of people who are not friends. Okay, let me try to visualize that. Imagine that you have friend one, friend two, friend three, and friend four. Okay, so friend one and friend two are friends, friend one and friend three are friends, then uh friend three and friend four are friends. Okay, well, let me just use that same idea. So friend two and friend four are friends. So what will be the complement graphs here? So from the definition, a graph that contains the same vertices as the original but has edges wherever the original graph does not. Okay, so imagine that this dotted one, these are edges now. So the complement graph here will simply be um, F1, F2, F3, F4. So you can see the nodes are intact, the vertices are intact, but now we have only this and this. So that is the complement graph. Okay, so this is the graph, whereas this is the complement of the graph. So same vertices, but different edges, basically. And that is the idea there. Okay, so with this, let me see. Maybe there are some final remarks. So, I mean, by understanding these properties, we can analyze and model complex systems such as networks, transportation systems, or social interactions in terms of their structure and relationships. I feel like I need to write that. I think it's important. So by understanding these properties like degrees, path cycles and all that, connectivity, and then now subgraphs, induced subgraphs and complement. Understanding these properties, one can analyze, one can the analyze, right? And analyze and model complex systems complex systems such as networks, such as networks, transportation systems, or social interactions in terms of their structure, in terms of their structure and relationships. All right. So if you have not subscribed to this channel, be sure to do that because there's a lot more coming your way. And hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know if you want me to teach a topic or solve a problem. and like and share so that more people can have access to this great content. Till I come your way again, keep getting network.